So thanks a lot to organizers. I'm really happy to be here in Sofia. It's my first time in the city. It's really beautiful. And I'm also enjoying this workshop so far. For the ease of mind of everybody, I'm replacing a professor. Yes, he's performing a surgery, not under surgery. He's fine. He will be fine with us later. And today I want to talk about a couple of our later projects in the lab in Bern. Later today, Mihai will present some other of our projects. And these ones are a bit maybe more theoretical. We will see how it goes. I try to adapt to what I thought the audience would be. We will see if I succeeded or not. And the topic is, well, propagating error through space, time, and the brain. And a big emphasis will be on this temporal aspect. As Sonia was saying already, and it seems to be a bit a topic today at least, brains have to do temporal processing. It's one of the most interesting things that brains do. And when we want to learn from the brain or understand the brain and using or connecting it to deep learning, we always arrive at this issue of like, okay, how do we do what is called credit assignment in the brain? So we have a deep neural network, we have some inputs, we have some outcome, some behavior or whatever, and we would want to adapt this behavior to reduce the cost, we call it in our lingo. And therefore we have to say, okay, no, we did something wrong, therefore we have to correct what the neurons did earlier in the network, and we have to assign the error proportionally to each neuron. This is the credit assignment problem. It's very easy to solve. Or like there are well-known methods to solve it in artificial neural networks. It's not so easy to solve it in a biologically plausible way or in neuromorphic hardware. Because what we are interested here, as the title of the slide, is deep learning in physical systems. And physical systems come with constraints. So yeah, basically what I was saying, like the normal, the typical way that we would do that in an artificial neural network is what is called backpropagation of errors. And it, we want to learn a specific map from some input space to some output of action, so whatever. Supposedly here, for example, a classification task. And, well, the usual way we do it is in this sense, but physics has this constraint, and the constraint is what we call locality. And basically what we want is that dynamics and learning in the network should only depend on what is happening in each place and at each moment in time. So each neuron in the deep network should only need information that is available to it in each moment in time. That's locality in time, and in each place. Of course, I can use the network to transfer information, but at each moment in time, I can only use the information that I have now here. And there is bonus points for our task if we do this in an online way. That means that we are adapting the weights of the network to learn the task we want to do without having to do phases, without having to do an action and then wait while we correct all the weights and then do another action and wait while we correct weights, but correct weights at the same time as we are doing actions. This is called online learning, and it's what we mostly know the brain to be doing for some tasks at least. Okay, so our problem is then this credit assignment problem, and in particular in problems or in tasks that have certain temporality. For example, now I'm talking to you, you have to process the sentence I'm telling you, and therefore you need to have some certain memory of the word I said before, and this requires to solve a problem that has a temporal component. And yeah, sentence processing, for example, word recognition. For this class of problems, the cost function that we will decide, that's it. That means the function that the way that we will define what the error is like, if I am doing the things perfectly, the cost will be 0. If I am erring, there will be a cost to my action that then I will transmit through the network, telling each neuron, hey, this is the cost, like you are incurring a certain cost. I will need to integrate it over time because it will be a temporal task. And I'm interested in minimizing, in making a cost minimum that is like not, and like it's not like when I recognize a picture of a cat or of a dog, it's just like, see the picture, tell me if it's a cat or a dog. When I'm recognizing a sentence, it's like there is a whole temporal structure, and what I want to minimize will be given by a sum or an integral over time of a certain desired behavior with respect to the behavior of the network, of the output layer of the network, for example. Okay. For this first part of the talk, I will be, like the brain is super complex, so I will just be looking at feed-forward kind of networks, and I also looking at Bleak integrators. Like I will be talking about rates and not about spikes. Later on in the talk, I will go to spiking networks and eventually, hopefully, to hardware if I have enough time. But all this that I'm presenting now, I will develop in terms of rates. Okay, so a little of mathematics, because I was told that the audience were a lot of mathematicians. But this basically is like, this comes from this very nice paper. And it's like, well, if I want to do temporal data assignment, there are basically 2 ways of doing it. One is like looking at the past, and one is like looking at the future. And I won't go into the details. It doesn't matter too much. It's more like a nice picture. But the basic idea, and sorry for the change of notation, what I call the cost here is called the loss, just because I took this figure from the paper. But the basic idea is that if I want to improve the performance of the network, I will minimize the cost by changing the weights inside the network. That is like the great assignment problem that I have. The loss or the cost is integrated over time. So I have like the total cost is a sum from now to the end of the task of a certain cost that depends on the time. So I have like an integral over time. But inside that integral over time, I have another integral over time that is like how the past state of the network influences the present, for example. That's the past-facing approach. But then, because you basically have a double integral in time, you can make a change of variables and represent the same thing as how will what I do now affect the error in the future at the output. So those are the 2 ways of expressing this loss function to try to minimize it by, for example, gradient descent. It's a picture. I will go to what are the main contestants in this forward versus past facing. In the case of the future facing algorithms, we will find out it's just like an old friend, but it's called backpropagation through time. So what we have, let's say, we have a certain chain of like feed-forward neurons, and this is the advancement in time. The way that backpropagation through time works is that I will change I will calculate what is the gradient of the cost with respect to a weight by checking how, if I change the weight now, the error will be in the future. Of course, this is a kind of like the causality is wrong. So what backpropagation, when actually applied, is doing is like you run the thing, and then you wait. You don't do it online. Wait, you check. Okay, 10 time steps before, I did something that messed up my cost now. So in fact, 10 time steps before, I should have changed the weight, and that's what I will do it now. So I go back, I repeat, I do another trial, changing that weight. But at the level of the mathematics, what backpropagation through time is needing to work is a prediction of, or an exact prediction of what will be the error in the future if I change a certain weight here. Like I'm neuron 3, if I change my weight to neuron 7, what will happen 10 seconds into the future? Of course, if it's a lot into the future, maybe it will affect very slowly, or like in a very low, in a very little way, small way, that's the word. And this function is basically, there will be an explicit expression later. Basically, it's like a low-pass filter to the future. So what I do now will affect a lot the error immediately afterwards, and maybe will affect less later on. That's a detail. What matters is that at the basis of PPTT is this need of knowing, of being able to predict with complete or as much precision as possible the future. Of course, you cannot do that. So what you do is like you wait until the future, and then you run again with the knowledge of the future that you gain. And of course, you have to iterate if you do it that way. There is also past-facing algorithms, and these are like a bit more biologically plausible, because these ones you can do in an online way. Your network is evolving, and you are like looking at what you did in the past that affects your error now. And this sounds like a good way to do it, to change things in an online fashion. Now, the problem is like, if you rewrite the cost equation to obtain that, you will find out that what the history that you need to know is the history of how all the rates are affected by the whole history of weights in the whole network in the past. So in principle, if you have a lot of memory, you can store all that information about the past activities and about the influence of each weight on your present. But of course, that's a lot of memory. It's like order n to the cube in memory. You need to store information for each neuron about how all the connections in the network affect the activity of that neuron. And yeah, because of the way the algorithm works, it's also order n to the 4th in computation. Now, for small networks, this is not a big issue, or else you perform some sort of approximation of this to simplify these memory requirements, to simplify these computational requirements. And eProb, we heard about it today, is one possible recipe or like approximation mechanism or systematization of an approximation that allows you to do this kind of task in an online, biologically plausible way. But it's not the only one. We have another one, and we are evangelizing about that. So backpropagation through time uses the future error and the present state, but you cannot, realistically, you cannot do it in an online way. RTRL uses the present error with the past state, but you need a lot of memory, or you need approximations. What we propose is called generalized latent equilibrium, and it uses information that we have now and the state that we have now. Of course, there's an approximation involved here too. Like, we don't have a crystal ball that is perfect and that allows us to know the future with total certitude, like BPTT requires, but we know that neurons, biological neurons, do perform predictions, short-term predictions or first-order predictions of what will happen in the future. And we can use that information to approximate what BPT will do, to approximate what will be the activity in the future, and then let, deep learning do its magic. Like, we know that we will be approximating, but we also know that deep learning can work magic sometimes, and this approximation allows us, and we know how, like we control how far off we are from the exact error, will allow us to find an approximation that is a solution, a learning procedure to solve the credit assignment problem in a temporal task that is online, that doesn't use more memory than like local, like order n memory, and that also, as you will see, is cheap computation. Okay, so let's go there. Just a parenthesis for the mathematicians among us, but maybe I will skip this. So as I was saying, there is temporal computation already happening in biological neurons. We know about that. The easy way, like the example, is that neural membranes are low-pass filters. Like if we take a leaky integrator model of a neuron, we know that its basic solution is the low-pass filter of its input with a certain membrane time constant tau n. And if we look at the difference between for example, a sinusoidal input and what happens with the output, we see that there is a certain lag, a certain temporal lag with respect between the input and the output. And this, in a way, works as a short-term memory of what happened before. What happened before was this input, and now the information about this input is in the neuron a bit later. So this is a very simple temporal processing example, but this is happening, like we know this happens, but this is not all that is happening. There is an inverse thing going on in biological neuron, and this we know from measurements, is that neurons also, some neurons also perform what we call prospective coding, and this is a bit less well known, maybe, or a little bit less universally recognized, but neurons can react to their input in a slightly advanced way, and they do it with reacting not only to the input but by the speed with which the input is changing. So if we look at the plot here, it works like this: like the input is changing, and then the output not only reacts to the input, but kind of overreacts to this increase in the input, and therefore the complete output comes before in time. And this has been observed. I'm coming here right now. It's the second. It's the next slide. So, okay. So we first, like you can see it already in depending on the parameters and how you stimulate in the Hodgkin and Huxley model, you can see this kind of behavior of an output coming before or like, yeah. But the best indication for us were these experiments 20 years ago with sinusoidal inputs, in which using pyramidal neurons, this kind of temporal shift was observed in the output rate. So you have a certain, like, there is noise, but you have a sinusoidal modulation, and the spiking of the output spikes are advanced or have a certain phase advance with respect to the input. There is also more recent work with respect to that study how adaptation threshold adaptation, for example, affect the temporal properties of the output of the neuron. And in that case, too, one observes that one can obtain a certain amount of this effect, this temporal advancement. We have a recent publication with Simon, one of our students, where we did a very simulation-based inference analysis of Hodgkin-Huxley, and also of our more simplified models of leak integrators, where we see that this effect is very robust. That given not all neurons, but given the right parameters, you obtain neurons that fire prospectively, as we say, or it's kind of like overreact to the input. And this is a general effect that you can see in signals processing. If you have like some sort of adaptation mechanism, then you can be sensitive not only to the input, but to how the input is changing in time, which makes you overreact. Yes? Yeah.
Let's have a hard threshold.
Yeah.
And noisy sub-threshold.
Yes. This is also, yes. Yes, this is also an effect for noisy systems. Yes, this is also well known. Yes, but even in the case without noise, you can find it if you have this adaptation mechanism. Yes. So we have all these elements. We have the need to predict the future and to remember the past. We have neurons that can, for short time scales, do exactly that. And we have deep learning that is making many neurons work together and use all their capabilities together. So with all of those ingredients, we propose this method that indeed tries to find a way, or like the shortest way to say it is like we can approximate BPTT in a biologically plausible way, fully local, without phases, and using this biologically inspired information. So the way it works is like, it's kind of like we did this thing because we come from physics, in which we are doing a first principles approach. These are our building blocks. These are the things that we start with, and then we show that we can reproduce the results from BPTT, for example. What we have is what we call an energy function that looks like this. It consists of some local error at the level of each individual neuron, and a term that takes into account the cost. When I try to minimize this energy, or like minimize this energy, what will happen is that each individual neuron will try to minimize its own error. I will define exactly what this error is, but it's kind of a frustration of the neuron of not being doing what it's supposed to be doing. And I will also be trying to minimize this cost function that I defined. That is a function of time. And once we have this energy, we will define plasticity as a local gradient descent on the energy. So I will find a way, a very easy way, I will show later, of changing each individual weights, only using information that is available locally, by finding the derivative of this neuron energy with respect to each weight. This comes with certain set of experimental predictions. So like prospectivity has to be there. I have to find prospectivity for this to be true, but like we strongly believe it's there, and it has been seen experimentally in some cases. But what is really nice also is that the formalism itself suggests like a natural microcircuit implementation in which we will have some forward inference neurons, and in blue, some neurons that will bring back the error from the output layer. This way is that I will be able to have only all the information I need at a local level. The neurons are also not point neurons explicitly, but they have 3 compartments. They will have like a somatic compartment and also a basal compartment where information will arrive, and an apical compartment, like we are supposed to be modeling pyramidal neurons, where the error information will arrive. And then the comparison between the apical information of error and the somatic information about what is coming from below will be driving the dynamics. And I will talk about the dynamics right away. So if we double click a bit on what this network energy looks like, it will look like this. And I should have maybe presented the notation a bit better, but anyway, like it's a sum over each and every neuron of like what comes, what comes into it. So like this is the U represents the potential or like the voltage of each neuron, and the symbology I should have explained before. Sorry, like this breve thing is the prospectivity operator with a certain time constant, which will be the membrane time constant here, or a rate time constant for the outputs. Like the outputs are prospective with a certain time constant, and the membrane time constant also performs a bit of this prospective operator. By differentiating what comes into what I'm doing, I will have a certain frustration of not being doing what I'm supposed to be doing, with a certain nudging from the very top with this cost function. The beta is a small number that allows me to nudge the neuron towards minimizing the cost. Yes?
So UJR, is this the membrane potential, like the potential operator? Is the membrane potential of another neuron?
Yes.
So,
I'm summing, I'm summing over,
yeah, why does it have
Yes. So, I'm sorry, like I realize I'm not, so the R is the output. So each soma outputs a certain rate. And the soma performs this prospectivity operation with a certain time constant that is not necessarily the membrane time constant. When I receive information, I'm dealing with my input, then I have a membrane time constant and I need to compensate for it. But when I'm doing an output, I'm doing a prediction with a, in principle, different time constant, which is a like output time constant.
That means you don't calculate two perspectives.
Yes. Well, yes. Sorry. Yeah.
Like one with time constant R.
It's not exactly that. Sorry, I'm explaining this wrong, and I'm feeling a bit bad.
Why don't you show us the differential equation for the normal?
Yes. They should. Yeah. Sorry.
I mean, you can also write them on the blackboard if you have.
Yes. No. Yeah. Yes. Sorry. So these are the differential equations. Sorry, like so yeah, this is a leak integrator, and yes, so this is the rate that is coming from the previous neurons, and there is an error term that will be will be connected to what the next neuron is doing. Yes. So the issue is like this. I'm sorry. When I make like the neuron dynamics will come from minimizing this energy. When I make the minimization of the energy, I will find cross terms, and some will come from below, and some will come from the neurons that are like before me, and some will come from the neurons that are after me in the network. Okay, that's clear. Now, each output will have like in principle, its own prospectivity like effect with a certain time constant tau r, which is the output prospectivity. Let's say like I send information trying to, in principle, compensate for or like to predict the future.
And this is, I think, where I have to take ownership on the mistake. Which is the axon of the neuron on the right. It's a file of new bread.
Yeah, here is R. Yeah, here is R.
That's my mistake. So indeed, each neuron has only one perspective time constant at the output, which is bread R. Bread M doesn't really exist in that. If you take this energy and derive dynamics from gradient descent on the energy from this particular special kind of, you get the low pass filter. The bread M kind of becomes a low pass filter. Yes. But the bread M doesn't exist anywhere unless, with the exception of this abstract thing.
Okay, so like it's not a variable in your neural model.
Yeah, no,
it's just like it comes out from the mathematics and then you call it.
Exactly. Sorry. Only now I understood your question. Yes, exactly. Sorry.
Sorry for the.
No, sorry. I am sorry. I misunderstood the question completely. Good.
And what I know is that blobs, there are two blobs.
Yes.
And this triangle in the middle.
Yes.
They are just conception. So they don't have their own membrane voltage state.
No, I mean,
Like
this is
the compartmental model.
Yes.
Which this symbol here indicates.
Yes.
You would have three state variables.
Yes.
One for each compartment.
You do.
You don't.
No, you do.
Okay.
But it's like each like the terms in the equation are in different parts of the neuron, and that way I have all the information locally, but each like by making several parts of the information in different places, I can make the whole thing local. But that's the whole trick. But yeah, each part has a different piece of information. So I will explain this figure later, but for now, this is the way in which we connect this neuron one with the other. So we will have like, as we see here, an input where this thing is processed. That each neuron will have like its own voltage here, and the error information will be stored in the apical dendrite. And then this, this ensures that as I said before, that everything is local, and it ensures that this neuron here can have the information from the output that I need. And for that, I have these error neurons bringing back that information. And also these error neurons are performing these temporal operations in a way that, for example, if in the case that I would have only low pass filtering here, like the error neurons will try to compensate that by being only prospective, so that in the end, the information about the error that I have locally in each neuron has the right, let's say, the right temporality, or like it's synchronized. Yes.
You got that for the line.
Yes.
In this equation, on the bottom.
Yes. Yes.
I want to take all first simultaneously is valid, or mustn't there be some time delay?
Yes. the idea is that this works online, like for each temporal, at time t, I have all this information together. Now, of course, when we are doing this, the simulations, we do simulations in discrete time with very small dt. And in those cases, sometimes we have to be careful about like that everything is in the same t. It can be like, you know, kind of subtleties there, but the physics is clear. Like all of this has to be evaluated at time t. And it better be like the information better arrive at that time. Yeah.
But you now still have a backpropagating error.
Yes.
But you want to avoid this.
I have about propagating error. Exactly. And that's what I need to have this information. What is happening is like I am processing the information with the red neurons, and I'm sending back error informations with the blue neurons and combining it so that it at the same time affects the weights. As I am doing, I am learning with this information that is coming from above. So this is I have to do it, and it's you know, it's maybe like, you know, I have double the numbers of neurons that some other people would need, but I'm able to learn online. I'm able to do and learn at the same time.
Question,
yeah,
also relates to the biological plausibility, right? Of how the error is transformed. And if you look at the equation on the bottom, what the error neurons do is they just send their information forward through synapses. So this is why the blue things are also shaped like the red things. These are actual pyramidal cells with applicable or basal compartments, which do an integration and a prospectivity. So the same thing as in the forward pathway, only with different parameters. But it's still just normal neurons integrating information and sending it forward. The only difference is the 5 prime, which is still there. So this is called a multiplicative gating via STP, right? So this is the only additional element that comes in, where neurons don't just sum the information of their respective partners, but there's also some lateral combination, which you definitely have throughout cells.
So coming back to the biology, I mean, I still see a WL+1 post.
Yes, we come there. We come there. Because that's the weak spot. Exactly. That's what is still non-local. But before we come there, let me say some nice things about it. So as I was saying at the beginning, like that we want to approximate BPTT, and we can show mathematically that indeed the change in weights that we calculate with our method is an approximation of the one that BPTT would calculate with its method. Not only that, but if we do a Fourier decomposition and we see like what happens at each frequency, we can show that in fact the phase shift of like our error is the correct phase shift, but the gain is wrong. Now, because we are in a deep neural network, having little error in gains is not the worst thing that can happen. So it's quite controlled, and the phase shift, which is where most of the temporal information is correct. So that's like really the power of the method comes from this having a very controlled approximation of what the exact solution would look like. Yeah, I need to hurry a bit, sorry. So this is the way, like the comparison with PPTT, I think is basically what I said. Now here we have like this is BPTT. We call it the adjoint method because it's an equivalent way of seeing BPTT. And here we see for like just a line of neurons that have to do a task, how like our loss really approximates, like this is a simple task teacher-student neuron, how we really approximate the BPTT target. Here we have an explanation of what we are doing. And in BPTT, of course, by doing it in not online, what we do is like we see what the loss is, we change the weights, we do like, it's like a global change in the weights. We have like, we can imagine this space where we have like a cost function that we want to minimize, but we also have like a trajectory in time. So it's multidimensional in that sense. Like we have an input, we have the output rates. What BPTT is doing is like calculating the cost, the integrated cost, and then modifying the weights. We are modifying the weights as we are doing the task. So this is different, and it's of course an approximation because we cannot know the whole future. But because what we are erring is in the gains, like we trust that we can reach the correct minimum for the cost function, and we show that we do. So this is nice. Like for example, what this allows us to do is spatiotemporal processing. Like, for example, only with taking into account like low pass filtering, we can see like if we have like a temporal signal and a spatiotemporal signal, we can use these neurons with different temporality, like with different values of this temporal constants to have information about different temporal windows. So in a way, we can make them work as the word scale. Sorry. Anyway, like we can, yes. So the types of problems we have solved with this are like, for example, temporal problems. This is what is called MNIST-1D. You have the digits of the MNIST database, and you can convert them into, like by some mathematical transformation, into a one-dimensional representation. So the 0 looks like that, or the 1 looks like that. You can see there is something from the two-dimensional image like this is an example of each class. And we can process this as if it was a temporal signal. Now, this is quite complicated because the way this database is made is like the actual signal is only like a little piece of the full sample. So you have to either have good memory to know when the relevant part was, or like not paying attention for a while and then paying attention, these kind of things. So it's a good test for something that has to do temporal processing. And indeed, we are there at we reach levels very similar to the best the best architectures available in the literature, like temporal convolutional networks or GRUs, and we are much better than a linear perceptron. For all the other methods, except the GRUs, like this is a spatial problem. It's like we give them the whole signal, and for us, it's like it's an online in-time learning. And online, we also see it here, like how we are learning with as we are training the network. We did something that is a bit more complicated, that is Google speech commands. And this is like a database made by Google of words spoken by people, and the word Google or like the word hello. And you can learn to classify. Because it's people speaking, there are many frequencies. It's not only one-dimensional signal, but there is a combination of many frequencies. And again, we reach almost state-of-the-art performance in an online fashion, and with, in general, using, I didn't put the values here, but using less parameters. Like it's also a very efficient method. we also use this to process chaotic time series. In this case, is the Mackey-Glass equation. It's one of the simplest chaotic equations you can have, and it's chaotic because it has some dependency. I didn't write the equation. It has some dependency on the past, or like on different time steps of like it's a differential equation with dependency on not only on the now but on different time steps. And we could train our GLE neuron to learn to reproduce during several Lyapunov time scales, like the behavior of this chaotic system. And this is a classic way of testing temporal processing capabilities. And we did very well, and we have new results that are even better, but I won't enter into the details. Because we can do time and space, we can also solve spatial problems, and this we had solved before in what was then called LE. Now this is the generalized version that includes time, but we can still do the spatial aspects, and we do super well. We can classify images, we can classify finding the Higgs boson, etc. But we still have a source of non-locality, which is that, in fact, our backward neuron needs to know the weights of the forward neuron. And this is, of course, non-local, like I need to know what happens maybe on the other side of the brain. And have the exact same value. Like, it's very unrealistic, or like very not biologically plausible. Luckily, we have, in parallel, we developed a method to align the weights, and we called it faceless alignment learning. We also have a spiking version that is called spiking aligning learning, hopefully. I don't remember the name. DS, but it's SAL. I wanted into a lot of detail, but the basic idea is that I can add, I can start with a random or like a different weight for the backward path, and I can have a learning rule that not only learns the task I want to learn, but in parallel learns to reproduce the forward weight. And in order to do that, it's like the trick basically is that I can send noise, Poisson noise, for example, and noise has this nice property that it only autocorrelates well with itself. And using that property, I can learn, like, at a distance, what is the weight that I'm trying to copy. And I can learn at the same time, or I could do phases, but in principle, this is tested in these papers, that you can even learn at the same time as your task, and it quickly goes to where you want it to go. So this is super nice. You should check it too. So for GLE, we have this way of approximating BPTT that uses things that we know from biology. Like we have that neuronal can do retrospection by low-pass filtering. Neurons can be perspective, and this is a known property that we are trying to make it more known, and it allows us to approximate BPTT error signals. And the computations that are done here are plausible for biology and neuromorphic hardware if we add this faceless alignment learning. And we use neuron local plasticity. It doesn't have faces, and it scales in memory and in computational with the number of neurons. So it's really nice. Now, depending on the time, I have more things to say. This will be one part of the talk. I don't know. It's fine. Okay.